Hello, everyone. Thank you for joining us for another AEE monthly member webinar. I hope you are all having a great day so far. Before I introduce our speaker, I just want to go over a few announcements. Following the webinar, you will receive an email with a certificate of attendance and a recording of the webinar. If you are interested in obtaining a copy of the presentation, please email me at cheyenne@aeecenter.org. I've also put a copy of my email address on the PowerPoint. We will be doing a Q&A following the presentation, so please place any questions in the question box on your side panel. Without further delay, I would like to introduce today's speaker, Mr. Bill Taylor. Mr. Taylor will be presenting on Developing Energy Resilience, a Roadmap. Bill is an engineering manager for Systems Energy Group's Federal Business Unit. His primary focus is resiliency and new technology solutions. In this role, Bill leads the evaluation, solution development, and implementation for resiliency and innovative solutions for ESG customers under multiple forms of procurement. Bill has over 30 years of engineering experience in a range of industries, but always with a focus around energy-based solutions. Before joining Energy Systems Group, Bill worked for an ESCO as the engineering operations leader. In this role, Bill provided complete energy solutions to a wide range of clients, including the U.S. federal government, municipalities, school systems, universities, healthcare clients, and industrial clients. The energy solutions provided included renewable power generation, smart grid and microgrid development, and critical infrastructure updates. Bill is the author and co-author of over 20 technical papers and holds 5 U.S. patents. Bill holds a Bachelor of Science degree in Mechanical Engineering from the University of Utah and a Master's of Science degree in Mechanical Engineering from the University of Washington. Bill is a licensed professional engineer and a certified energy manager. I want to quickly thank Mr. Taylor for volunteering to present a webinar with us, and I will now be switching my screen over for Bill to begin his presentation.
Thank you, Cheyenne. Appreciate that. Let's see. Hopefully everybody can now see my monitor that says on the opening screen. I'm pretty sure that's correct. So without further ado, shall we start? And I want to thank everybody for joining this afternoon. Let's see now, and I can't seem to gotta play this. Give me a sec. Agenda we're going to go over quickly what resiliency is, what the mission is, requirements, what I mean by gap analysis, controls, financial considerations, because ultimately you do have to pay for resilience. Lessons I've learned, at least some of them certainly in the near term, and we'll have time hopefully at the end for some questions and answers. A lot of classic definitions out there for what resiliency means. I will make this address. I'm in the Federal Business Unit at Energy Systems Group. So that I originally wrote this with the definition from DoD, modified a little bit, but this will be, I'll make sure that I address this to the municipalities, universities, school systems, any cluster of buildings that you like to add resiliency to. Basic definition is to recover from and continue operations during any kind of utility operations. I don't mean that the entire focus is on all the buildings, all the functions are going to work with that, and you have to actually categorize what you're critical and what you're not. You can categorize, and this is one of the big questions, how long your interruption of utility power, and it could be water, could be wastewater, could just be power, could be natural gas service, could be a lot of things. What are you going to consider that interruption to be? Is it a one-day storm, you're out for 2 or 3 hours? Okay. Is it out for a week, 2 weeks, like it was with Hurricane Sandy here on the East Coast? So those questions start to impact and start thinking about what do we mean by resiliency and how are we going to categorize that. Start to categorize it by what the mission is. The mission is really why the facility, a group of buildings, why they exist. If it's a university, They primarily exist, I would think, to teach the classrooms, instruction, research, potentially, and it could be attending football games or basketball games. If you're in the middle of a national championship, you don't want the lights to go out. So understanding why the facility or the reservation, if you will, the cluster of buildings exist is incredibly important. Once you understand or begin to understand that mission, what is required to make sure that mission is executable should you lose utility power or utilities in general? And you start asking questions, because the first part of any solution is asking questions. Which buildings? Which buildings do I need to power if I lose power? Which buildings do I need to make sure can be occupied? Which buildings do I need if I have on-site personnel? Which support functions? Do I need something besides electric power back on? Do I need to have water? What happens if I need water for cooling systems? What do I have to power up? What has to operate in a utility crisis? And which personnel? Who has to be on site? Who has to be able to function? Who has to work? Who has to attend classes if it's a university? If it's a municipal center, what do you want to do? Is it a place where residents can find refuge? They can charge their iPhones or their Samsungs? What is the purpose? What are you trying to accomplish? What are you guarding against? If you're going to have resilience, you're guarding against a failure of some kind. What is that failure? Is it a substation fails? You no longer have electric power to the system? Is a natural gas line ruptured in some fashion? And certain things I've worked on in the past was university, and they said it can't be natural gas because in this particular state, in the emergency, natural gas is shut down. And energy flexibility is a big thing. Do I need the same amount of resilient power, functions, etc. on day one as I do on day 7, 10, 14, 15, or longer? Understand how things can change over time. Mission support functions, I mean, everybody thinks about what does it mean if I want resilience? They immediately go, I need electrical power. And I see that every day. Saw today on something. It's more than that. Electrical power, you can think of, okay, I got on-site generation. Maybe I have some renewables, maybe wind or solar on site. Well, that's okay. Can I use that if I lose the utility? Typically not, unless you plan for it. You have battery storage, thermal storage, you have portable power. A lot of military bases have diesel generators that they can actually tow behind a Jeep and go power up a building if they have the right connectors. One of the interesting things is that if you have a rail yard on your facility, and a lot of older schools, a lot of older facilities do have rail yard, there's a locomotive on site, there's 600 kW to a megawatt of power sitting there in the diesel generator. Can you access? Wastewater. I have to use it. I mean, people are going to be on site. You gotta account for their creature comforts. Is it on site? Do you have one? If so, do I have to power it? Is it portable? Am I going to have porta potties? Am I going to have pumping power to get it off site? And if I pump it off site, can they accept it? Water supply gets into the same type of question marks. If it's on-site storage, is it maintained? Is it clean? Is it potable? If it's not, do I have to run it through a water treatment facility? In which case, I have to power that as well. Electric power, if I'm going to have on-site generation that requires fuel, what am I using for fuel and how am I going to store that, or how am I going to deliver it? Diesel's the go-to, but there's propane out there you can store. Some of the systems run on that, liquid natural gas. But now once I do that, how am I going to store it? How do I maintain it? Liquid natural gas boils off, it's a cryogen. So now I have to use the boil off, or I'm just putting it in the atmosphere, which doesn't do anybody any good. And how do I resupply? Does my supply on site last as long as I think I want to plan for an outage? Communications. You want to talk to the outside world, command and control if it's a military installation or a government facility. Mission critical. Do I have a data center on site that needs to communicate? How do I keep that up and operational? How do I have a facility-wide, if I have a building control system, energy management control system on site? What do I do with that? I can use that if I can power it, because I can now create demand reductions on command while I'm maintaining critical facilities during an outage. Do I want my cell phones powered up? Do I want cell phone towers powered up? Computers, do I want to do that? Well, now I got communications. If I'm talking to the outside world, Cybersecurity is not just for government facilities. I would say that most facilities out there have some form of cybersecurity, down to my cell phone has my malware system on it. My computer certainly does. Controls, building management systems, so I want to link into that in some fashion or design so I can link into it. I have a microgrid. How am I going to communicate with that? How am I communicating status back? Switchgear, I need to be able to command that in some fashion if I'm going to automate anything. Okay? Circuit upgrades, what do I have to do? All this feeds into, I want to keep my facility open for X number of days. Where to start? I always start by asking the right questions. Well, what are the right questions? Open-ended help a lot. Walking in and saying, hey, where do you want me to put my microgrid is probably not the right question to start with. It's understanding the problem and developing the requirements. Questions that go to that level now begin to help you formulate what the solution is. What are the needs of the mission? What's the needs of the critical function? Do they have a current resiliency plan? They have current equipment and current capability, or we kind of get into this into we don't have anything, we need to start from scratch. What is the desired resiliency plan? They obviously have a thought, otherwise you wouldn't be there as designers. Recognizing the gap from the base case. This is what they've asked for. Where are they? That gap is what we have to fill. Continuity of operations is a term that's used quite a bit. How's it assured? Is it said I have to have all my critical functions? That's great. Maybe they're spread all over. Can I consolidate them at all? Can I move things if I have a power outage to another building? Can I consolidate during an outage? The gap analysis from where you are, where the facility is, and where they want to be, that's the gap. The question is, how do you get there? And that gap defines the resiliency requirements. And each of those requirements will be unique to a facility. There's an old saying, probably not that old now, but if you've seen one microgrid or one resiliency plan, you've seen exactly one resilience plan or one microgrid. You haven't seen any more. You've seen one because they all change. You have a bag of tools, but every situation is unique. Every situation is its own. The gap analysis where certainly we as engineers are going to live. We need to define the requirements. As I pointed out before a couple slides ago, almost everybody focused on restoring power, but that's insufficient. You need support systems, and that's why defining the mission, the critical functionality is so important. That brings in with it, what support systems do you need? And then you have to figure out how to keep those online. So water treatment plants, you can have water storage. It may need to be treated before people can drink. Wastewater treatment plants, if you're going to have people on site for an extended period, 5 days, 7 days, 14 days longer, where they are doing a critical function, you got to deal with that too. Ones you don't always think about. Some of these campuses, college campuses, certainly military installations, certainly unique situations in municipalities where they have a confluence of government buildings. Traffic control, silly things. How do you keep the traffic lights going? How do I power them? How do I keep them functional, or I put somebody out there and direct traffic? It's all a plan. Question is, what are you going to do with it? Security lights. Do I have anything that needs to be secured? Am I going to keep my security lights functional during an outage? More than likely, the answer is yes. So how do I do that? How do I empower my security system? And there'll be 100 more questions like this as you dive down into the requirements and trying to fill those gaps. You want to understand what's on site. Do they have any existing capabilities? What's their condition and what's their function? Distribution systems. The electrical power systems tend to be neglected. They tend to be old. 30, 40 years old is not an uncommon system. If you're going to command those, they're probably going to have to be upgraded, but you have to understand what you need to command or how you're going to override those pieces of switchgear. Controls and cybersecurity, what are the requirements? Do I have to have controls? If I do I have to have cybersecurity? And how tight does that cybersecurity have to be? Portable power, we mentioned earlier. Is there any stationary backup power? The go-to is diesel generators. Looking at a site recently, they date back into the 1980s. Okay, probably not going to upgrade those much. They can rebuild the engine, but I really can't command and control those without a lot of work. So what's there? Are they brand new? I probably can command and control them a bit better. Are there any central utility plants I want to keep operational? Okay, if I do that, what's my reference points? Do I have a voltage and frequency so I can match the frequency of the grid without the grid being there? How do I deal with that? Is steam or chilled water essential to the function of to the critical functions of the mission? It all gets down into what I would say the software guys that I've worked with in the past call use cases. And it's going through each of the scenarios of how everything's going to work, of the what if questions, and detailing this is what's going to happen, this is what I need to happen. As you go through that exercise, and it's not an afternoon, by the way, it's going to be many days and multiple efforts, to understand what the holistic picture of the resiliency for this particular facility, reservation, group of buildings, whatever you want, is how it's going to function. Cannot overemphasize the requirement for collaborative design. If you go in there with a preferred solution, it's probably going to be wrong, to be honest. Collaborative design means you have to work with what the customer wants. I have a sign here in a grocery store near me that says the customer is always right. Rule number 2, if the customer is wrong, please see rule number 1. I can't overemphasize that in resiliency as well. The customer comes first with their mission. They understand it. They may not be able to tell you everything about it, but they know what it is when they touch it. The collaboration between the design team, the local utilities, whether that be water, wastewater, electrical, gas, the design team, the testing team is incredibly important. The gap analysis. You're starting to understand the facility now. You're starting to understand what they want, understand how they function, understand what they need. Now you got to figure this out. Okay, I understand what the mission is. I understand what has to continue. And if we lose power, we lose any utility. Okay, where do we start? What's your continuity of operation plans now? What are you going to do? What happens if this happens? You want to identify the critical services to maintain the continuity of operations plans of COOP. Are there any services off-site that you have to interface with? Do they have to be brought on-site to make this work, or can you live with it being off-site and the chance that it may be interrupted? If it's a Hurricane Sandy took out a wastewater treatment plant in Maryland, that was a big deal. Now what do you do? If you're a facility there in Maryland, there's a lot of them. Now what do you do? How far down are you going to drive in your quest to be resilient? How many options are you going to look at? And maybe out of this is not a single project. Maybe it's a stack of projects. Maybe it's a series of projects that you have to execute to get them to where they want to be. But this is where you identify that. You're identifying the critical buildings, what their function are. Can those functions be moved? Do they have to stay in that building? What are the facilities? Is there UPS? Is HVAC critical? In some parts of the world, in this country, it is very critical. So go to the desert Southwest, you're going to need AC. Excuse me, Northeast in wintertime, you're going to need heat of some sort. Might be able to live without cooling in the summertime, but you're definitely going to need heat in the wintertime. Is the COOP currently being achieved? They've outlined their continuity of operations plan. Are there holes in it? Is it being achieved? If they're happy with that, that's a do-nothing case. Okay, guys, you're all good. We'll see you later. There's nothing for us to do here because they're happy with what they have. But if they're not, and they're likely not going to be happy with that, and this COOP can be improved, what do you do? Well, there may be a resiliency scorecard. Those are becoming more and more prevalent. Maybe it's a carbon reduction plan at a university. Maybe it's a true scorecard from a DoD or a government installation. Maybe the municipality said that they create a scorecard with them. Here's my deficiencies. Here's what I think I'm good at. And it's simple. Red, yellow, green, right? Just like a stoplight. Shortfalls lead to the areas. I mean, when you don't have the COOP that you want, what shortfalls you have will directly point to whatever infrastructure you really need to go take a look at. You identify a shortfall, that's great. Hey, I've got this over here, I got to go fix that. You need to look at those holistically. Resilience is not a spot solution. It's not one size fits all. You really have to look at the entire facility and what's there, what's not there. Treat resilience as a system. What are the controls you need? What are the new hardware you need? What are the interfaces I'm going to have? Is it the electrical distribution system on a campus? What about the local utility? There's a substation probably feeding it. A lot of universities have at least one substation that's being fed. Is that your point of interface? If I interface there, do I have to give an interconnection agreement with the utility? You start to peel the onion back about what do I have to do to make this all happen? What are my water conditions? Is it on site? Is it pumped? Do I need to add storage? Wastewater, do I need to have porta potties available? Can I pump it off site? What if a wastewater treatment plant fails? What do I do with it? You start to look at how do I manage an entire infrastructure on a complete facility. Communications, supervisory and control data system, your SCADA system. What are you going to do with that? I included in that your building management systems if you need them. But maybe it's a control network for your chillers and boilers. What are you doing with that? How are you going to do it with that? Do I need to do anything with it? Communications go way beyond that. You need to have off-site communications. Maybe it's fire and police. Maybe it's others. Is there going to be a communication hub for a town where you want to get broadcast messages out in the form of an emergency? Is there any cybersecurity requirements that you don't want people hacking into your systems? You need to integrate with the site. Every site is unique. Every site in every state is unique. Every state has their own particular flavor of environmental protection, where you're located at, what you can and can't do, what your air permitting looks like if you're going to burn fossil fuels. The federal government has some, but we have 50 states, and every one of them has different requirements on what you can and cannot do. You need to look at what your fuel considerations. Do I have to store it on site? Do I need a backup fuel? If I want to run on natural gas, do I need to run on diesel? Do I need to run on propane? Do I need to run on liquid natural gas? Is it available? Is it nearby? How much do I have to store? Renewable energy, will it operate during loss of utility power? It'll operate, but without a reference voltage and frequency, you're not going to do much with it. You need to make sure you have that available. Usually, what we're doing now is using a battery energy storage system. On the inverter, we allow that to power our renewables on site. Portable generators are great. Some places have them hanging around and some don't, but they all have a pretty much universal connector. It's pretty cheap to put that universal connector into a building versus buying diesel or natural gas generators to fill the void. You need to interface to the electrical distribution system on the facility, but also you need to interface to how the utility gets its power on the site. You need that interconnection agreement. But do I need upgrades to my local facilities? The answer is typically yes. You need to do something. Maybe it's additive, maybe it's replaced, maybe it's both. Because you probably will have far more buildings on site than you want to power. So now you're going to have to start isolating buildings that you don't want to power. And that means you got to cut them off. Now that I've created this or started to look at these options, now how do I maintain it for a while? There's operation and maintenance. Is the staff on site capable of doing that? Are they going to be able to test on a monthly basis or quarterly basis or every 6 months or every year? And how are they going to test it? They're going to use a load bank if we have distributed generation. We're going to shut the power down and convert over to this. How are we going to do that to validate and to verify that when we need this system, it's fully functional? It's a big insurance policy that I've decided that this facility and this mission is critical enough, I can't let it go down in case of utility power loss. Okay? Doesn't matter what the reason is, I've now decided that's what I'm going to do. How am I going to ensure that it's there? I have an insurance policy, usually very expensive. I want to make sure that when the time comes, it operates. What's your test requirement? What's your operational maintenance requirements, your repair and replace requirements? If you're doing cybersecurity, and I'm going to talk primarily the government version here, but they exist in everything: financial industries, university systems. They safeguard data centers. The risk management framework and their updates. That's the process by which the federal government certifies that your SCADA system, your BMS system, your control systems can operate on site. Firmware and software updates. This is going to be a long-term investment. Diesel generators, I just mentioned, to go back 20, 30 years. That's pretty simple. You'll keep it as a turbine. I'm aware of still being used every day, that they think dates back to 1975, but they're not exactly sure of the date it was manufactured. And it's kind of an interesting history how it even came to be there. These things are going to last for a while. How do you update your firmware? how do you have to recertify now that on your control system that that updated firmware is good and is now past the cybersecurity? How do I test against new threats? How do I make sure everything is good to go? So as you ask all these questions, there's one other thing you probably ought to take a look at. We do like to look at visually at the problem. Tier 1 buildings is one of the common names we have for buildings that have to be up and operational in the event of total loss of power. Critical mission facilities could be anything. Here they're colored in red. Tier 2 buildings are a little different. Maybe these are dormitories. Maybe these are dining halls or cafeterias. Maybe they're a gymnasium that you want to power so people can take hot showers and work out the release and stress of multiple long days or whatever the case may be. Maybe it's a gathering center. People can charge their phones, their laptops, whatever they need. The question is, you want to look at this and say, well, how are these buildings related? Where's the feeder systems? Where's my electrical look at it? And as you start to look at it visually, you've got all these other things in your head. Now you start to lay it out and say, okay, now what can I do? You want to group the buildings, and you want to group them to a very large degree based on the electrical feeder system, if at all possible. I said microgrids are often associated with resiliency. That's a true statement. People often equate resiliency with a microgrid. That's not necessarily as true as it's a potential solution. Doesn't mean it is the solution. Could be. More than likely will be part of the solution, but may not be the whole thing. You can extend the use of existing assets, maybe a solar field, wind farm, diesel generators, maybe there's an on-site utility plant, etc. You can extend that. Can you use the continuity of operations process to say, okay, I have this critical function. It's in this building. It's not a big building, but it's kind of over here by itself. Well, if I lose all my power, can I pick up those laptops and move somewhere else, or do I have to do something to stay in that building? Is there a data center there I have to operate, which means I got to keep the power off? Maybe I don't want to move that. But if it's a different sort of a function, can I move that to another building without impacting the critical mission? That's a big deal. If you can do that, you're way ahead of the game. Electrical feeders, when you take a look at overlay on your critical building visual, you begin to overlay the electrical feeders of what buildings and how they interconnect to the critical functions, you begin to see a pattern very quickly of where you want to add power and how to do it in the most cost-effective fashion possible. Once you've got that, can the electrical system be modified? I'm going to want to command and control things. Guaranteed. In some fashion, I'm going to want to get command and control and probably not have a bunch of people running around in pickup trucks throwing switches to bring a microgrid up if that's what I'm going to do. What buildings am I going to isolate? How am I going to isolate them? Is that manual? Is it automatic? And what's going to happen when I island? I have now lost utility power. Now what do I do? How am I going to automate that? How am I going to take those particular buildings? Am I going to physically disconnect from the utility? As you begin to answer these questions, you now start to conceive of how you might want to bring in a microgrid into this. And I'm going to go back to a microgrid, even though it's not the end all and all, but like this picture, because it really goes into, I can use a central utility plant, and I'll show you one in a little bit. Microgrid islanding, what do I do with that? Smart grid, add energy storage, add renewables, add building optimization, add security. All these factor into what kind of control system am I going to use? And there's 100 different architectures. What one you decide, whether it's a tiered or distributed or PLC or PC based or some combination. What drives the choice? That drive is driven by the actual requirements you develop back in the gap analysis. What do I have to achieve? What are my requirements? How do I get from point A to point B? And my controls are going to help bridge that gap. My time. What functions does the microgrid need to perform if we're doing that? What is the mission of the microgrid? During normal operation, what are you doing with it? You have this great insurance policy sitting there. Do you exercise it? You help pay for it by peak shaving, maybe demand reduction. You can do frequency regulation, you put a certain type of battery in there. How's it paid for? Are you going to use it, or is it just going to sit and you're only going to test it? Those are questions that need to feed back into the control system as well as the overall design. Typically in the work that I do, we have to pay for it. We have to find energy savings to pay for that microgrid. So yeah, we do go after tariff structures. And how do we take cost out and put that into upgrading infrastructure? What happens during an island event? How is it going to operate then? Who's going to operate it? Who's going to command it? What data inputs do you need? Probably total KW would make sense based on the buildings, based on, you probably don't want KWH because I'm going to put out KW and run it for however long I have to. Power outage, I want to detect it. I don't want somebody to tell me, hey, we lost power. No, I want my system to detect it because it's much faster than I am. Health check. This insurance policy is going to sit there for X number of weeks, months, however, before it's exercised. How are you going to do a health check on it periodically? The ones that we're currently designing, which are very large, there's an automatic health check every few seconds. It runs through a litany. It's on a continuous loop. We dump the data, we look for faults. Then we go out and proactively take care of those faults. We make sure that system is 100% functional 100% of the time. Error codes, what do you do with them? You send out a broadcast, you send them a text, we can do it. You send it out to, hey, you got a problem here, it's 2 a.m. in the morning. Yeah, maybe you want to go wait till the morning, maybe you don't. You have somebody on 24/7 call. What are your human-machine interface inputs? What do you want the human to see? You're collecting all this data in the background. What charts do you want them to see? How do you want to evaluate that? How are you going to look at this? Who's going to get that data? Can you transmit that data? Can you take it off site? And you have to keep it on site. What are you going to do with that? All become questions about what are my controls going to look like? How am I going to look at them? Use cases. We talked about use cases a little while ago about how things operate. Well, now use cases are going to design the software. Typically, you have two. At least the stuff that I've been doing. Normal operation. Maybe it's peak shaving. I've predetermined the peak shaving, for those of you who aren't maybe aware of it. I have the predetermined total KW. In other words, I'm watching the KW. You're looking at value, slope, weather forecast, etc. You can turn the microgrid and power the components on to drop the demand so that you don't get paid a demand charge. A lot of the ones that we work with have ratchet charges, which means that the peak demand lasts, if you spend 20 megawatts, is your peak in July, and that's your peak for the year. You pay that whether you hit that again or not, but you pay it for the year forward. These are all pretty straightforward control algorithms. They're not new, they're not hard. You just need the data to say, okay, I'm going to go on now, and you go do it. Island mode, a little bit more interesting now. Still the power's lost. Critical buildings are isolated in the microgrid. You're going to bring the DER online, the distributed energy resources. Buildings are brought online as the DER powers up. You just don't turn on an engine and say, hey, you're going to take 2 megawatts. No, you're probably not going to do that. You bring them on slowly. Once the system's at full load, can you block load? You got to ramp it up. How do you handle that? And then you're going to manage the buildings. If I can take power from building A and give it to building B because building B needs it and building A does at the moment, that's fine. But as you go through all these questions, the largest number of use cases going to be, as you sit around the table and say, what happens if? And you start to think about the if question. What if cases are going to drive everything as far as your control systems go? When I used to work with and manage software, electromechanical software programs, the software engineers called the happy day scenario my normal operating. Everybody's happy, everything's working the way it should, and then they had the unhappy day scenarios. Unfortunately, the happy day scenarios number about 2 in most of these resilience programs. The unhappy day scenarios number about several hundred. I always pick a number 200. Not those 200 that I think of, because I can always say, what if the DER doesn't come online and one of my generators doesn't come online? What do I do? Building is not isolated properly. What's the software do? It's going to react instantly. Islanding is automated. How do we return to normal operations? If you're connected to a utility, say you cut out of a substation, and you've now detected power outage, you severed the link to the utility, you're going to go island mode. Well, utility comes back an hour later, 2 hours later, 2 weeks later. How do you go back? Do you do it automatically? A lot of utilities don't particularly care for that. What's the process? What does the controls do? Don't know. Who initiates the island? Is it automatic? If I detect a power loss for X number of minutes, do I island? If I detect it instantly, do I island? Do I island proactively based on a storm front coming? Interesting questions. How are transient loads handled? In other words, I'm going to power this up, but I have this many buildings I'm going to power. One we're designing now is over 100 buildings. How many do I bring up simultaneously? Probably not all of them. And how are the DER assets managed? The power varies. So you're going to do power matching with your distributed energy resources. How am I going to manage that? Who am I going to bring on first? Who am I going to bring on last? Am I matching run hours if I have multiple engines? Am I bringing solar on? Hey, the sun's going down. Now what do I do? Now I got to anticipate to bring other resources back on as I see the power drop from the solar array. These questions and their answers, they don't impact the controls. But the selection of hardware, how many people are going to have to operate this, to operate the microgrid and operate the resiliency? How many people do I need? Do I need one to watch it? Do I need 2 or 3 to go run out and stop and put out the forest fires? I don't know. But each facility, each installation, each university, they're all going to be very unique on how they wish to handle that. And that's going to also be related to somebody you're going to have to deal with is the offsite utility who normally supplies power, because they're going to have their own rules and regulations about how this works. The next line is diagnostic instrumentation. I would highly recommend you don't add that in at the end. You design that in from the start. You don't let the people that build it, you don't let the engineers who are going to go on site to try to do value engineering take it out. Because you're going to spend $10 up front in the design phase and a few more dollars in the production phase as you build the system. If you take those out, you're going to spend thousands, if not tens of thousands, trying to figure out what went wrong. It is money extremely well spent. The further up you can do this into the chain, whether it's a gas supply pressure, whether it's just the ignition, do I measure the incoming gas quality? What am I going to do with that? Do I measure my output? Do I manage voltage and frequency? How am I going to do that? Don't take that instrumentation away. You will need it, and I'll show you why here in a few minutes. Get back into the coordinated design and say collaborative design earlier. To me, they're synonymous. You need to involve everybody. It is not a one person makes it. The design firm, the customer, utility, that's a minimum. That's an absolute minimum. Probably have a control contractor, they have to be involved because this software is going to be customized to a particular facility. It's not, hey, I got this great control over here, does microgrids, does all this, manages everything. No, it's going to be customized. At some point, it will be customized. You want to make sure you can do that. And as they grow that product over the next 5, 10, 20 years, is it going to handle what I have now? It's not, I don't have to redo my hardware. It has to be compatible going forward. Operating systems are going to go out of vote. How do I make sure my system doesn't happen to it? And how do I make sure it's been checked so I don't have that problem going forward? Gets back into the cyber question. At some point in time, again, I use the military terms, the government terms, you need an authorization to operate any of these SCADA systems. You got to go through the risk management process. Have to. Whether it's university, it's going to be slightly different, but you're still going to have to meet their cybersecurity requirements and prove that you did so. And then it is safe. The worst thing you want to do is have somebody hack your microgrid right before it goes down, the power goes down, and you don't have anything. That kind of defeats the entire purpose. But it's not just the control system. Data links, if you're going to send data off-site, it has to be secure. You can't hack that either because it's the back door into your system. Your component health data, where am I putting it? How am I doing it? A lot of companies want to take it off-site. Is that valid? Do you want to do that? Are they cyber secure? And does that data link meet it? Does their security system where they're taking it off-site meet the requirements of your facility? Now, municipalities, it may be a lot less stringent than it is at a DoD facility. But the fact is they're still going to have requirements on how to deal with it. Your HMI, where are you going to put it? How am I going to, where am I going to put the data, am I going to allow who HMIs, am I going to mirror them somewhere where there's no control? They can't intercommand. They're just going to want to view the operation and how everything is sitting at that point in time. Or they want to issue commands from multiple sites or just from one site, and the others are mirrors that you can't control from. Big questions that all have implications on the control for the cyber aspects. And from a data standpoint, some of the facilities I work on, the distances between data from control point and the data where you want it to go can be large, not measured in feet, measured in miles. So you're not running fiber optics if it's not already there. How are you going to deal with that? What's your frequency? How are you going to communicate? If I got a substation that I can't run a fiber optic to, and my control station is 1.5 miles away, how do I get the data? Because I need that for peak shaving and control. So all these questions, as you start to peel back the onion on your design and resiliency, they all play into how this is going to work and function. As you start to assemble the pieces, and I've got my design now, I know what I'm going to go do, I've pretty much picked out my hardware, I got my controls, my use cases are pretty well set. I know my happy day scenarios, I got those, I'm rock solid on those. I got my unhappy day scenarios, at least the 200 I thought of, and we always worry about 201, the one we didn't think of. We'll find that later, I guarantee you at some point. But those are the ones that you deal with. I'm all set to go. Now what? Well, now you simulate. I've got my controls. I can start to put all those use cases on a simulation board, on a simulation program, on a simulation workbench, and start to test them. Do they work? Does my software work? Does my control architecture work? Does my control strategies work? And you'll start to find that, most of it does, and then the stuff that doesn't. You need to simulate that in software before you ever go to a control hardware integration. Once you've got the simulation working, you should have a test bench where you can do hardware in the loop testing. And then as where you had in software, you simulate, I send a command out to my controller, here's my model of my controller, and I accept a command back. And I accept a good command and a bad command, or a bad response. Okay, here's how I react. Now in place of that software simulated controller, PLC perhaps, I'm going to put the actual PLC I'm going to move out in the field. I'm going to put that in its place, and now I'm going to run the same test again and see if it does the same thing. If it doesn't, I need to modify it. I'm going to build that up control point by control point by control point. And I'm going to understand how that works. Then when I go to the factory functional testing of that, it's called a gas engine, and has a PLC on board, I now can test those same things by putting my software on top of that, on top of the factory testing, and make sure it does what it's supposed to do. As you build up each part of the components, as you build up each part of the hardware and the software together, you're going to build up a system. Always start the lowest possible subsystem and build up from there. Never add to it to that lowest subsystem is 100% checked out. Only when those subsystems have all been tested, they've all cleared, can you actually, the entire microgrid be tested. You don't want to find errors at the system level. You want to find it at the subsystem level, because tearing it apart from the system level to find it, you just added probably 6 weeks to 6 months to your project. By not putting the diagnostics in there so you can identify which subsystem it is you need to go check, you probably added the same amount of time. Hence, the diagnostics need to be in there from day one and never taken out. You really want to find those issues early. I spend $1 early versus $1,000 later on. That type of cost differential is real. People hear and they say, yeah, it's not really real. Yeah, it is. If it hasn't been tested, I can't say loudly enough, don't put it in the system. Okay, financially, how's it paid for? Easiest one is somebody writes you a check. Capital investment's always the best. But there's always going to be pressure to keep the cost down. If it's in a commercial industrial, I got a big factory. Shutting that down is pretty simple. I lose this much production a day, that equates to this much revenue per day, this much profit. I can now make an economic case for how much I can spend. Pretty straightforward. One of the other ways you do that is with an energy services performer contract or a utility energy service contract, both of which rely on I have to save energy and basically reduce your energy bill, your electric bill, water bill, gas bill, whatever. And I'm going to take those savings and I'm going to reinvest them in your infrastructure. It's an infrastructure renewal project is what it is. That's frequently how we pay for resiliency. You can find us from 25 years, some of that's a little longer now, and energy savings are guaranteed. So what does that mean? If we say we are going to save you $1,000, we only save you $900. The ESCO, the Energy Services Company, which is what Energy Systems Group is, writes you a check for the difference so that you are made whole. A couple of neat things about that. For the customer, they get a much lower interest rate than they would on any commercial venture because they're backed by an ESCO. And ESCOs really start when their balance sheet in the billions of dollars. This is not a cheap game. You have to have the funding to go do this. How else do we pay for it? Understanding the utility rates and the rate designs. The utility company is going to make their money to supply a lot of power to these large facilities, whether it's a university, whether it's a military base, whether it's the Social Security Administration in Washington. Pick something that's big that takes a lot of power. They may structure a rate for that, and it's going to look a lot different than what you pay in your normal utility bills or in your residential home. But the fact is, they're going to make their money one way or the other, whether it's on a straight KWH charge, it's a demand charge, a combination, or ratchet charge. They're going to make their money. Somewhere in that rate structure is where we can save money using the generation assets that we're putting on, or the resiliency assets may be a better word. Some of these contracts, and certainly the ESPC and the UESC, require the OMRR be built in. In other words, if we put a microgrid on site, we have to operate and maintain, repair, and replace it for the duration of the contract. That's also built into the contract. What they mean is that the contracting facility is not out any money. Everything is paid for by utility savings. So we put a microgrid in. Basically, it's about 11, almost 12 megawatts of power. It's on-site power generation. There's 2 solar turbines. Provides about 70% of this particular site, which is not set here, but it's Johnson Space Flight Center in Houston, which we back up. Provides about 30% of the site's base load, if you will, during a power outage. We use the waste heat from the turbines through a heat recovery steam generator. Produce steam for heating and dehumidification as well. We also can provide steam to do some steam turbine chillers. It can provide about, call it 50% of the peak chilled water load. Provides all the site steam load that you need. Can ILMO the Black Star capability and reduce the carbon footprint because it was much more efficient than what they were doing before. As with all of these, you get the basic functional schematic. We do have natural gas coming in, 2 turbines, heat recovery system produces steam. The steam can be sent back into the back pressure steam turbine, can go to a steam chiller, or can go to high pressure boilers and out to the steam load. Chilled water supply goes into some of the electric drive chillers if we need it. We can also dump out 125 psi steam and the 12.5 kV electric power back to the campus. This is the basic fundamental schematic. So what happened? Startup and early operation issues. Yep. Surprised it didn't turn on the right way the first time. Didn't operate the right way for the first time. Basically, we had, as part of this was an energy services performance contract. We guaranteed the output. Didn't quite make it. But on the good side, it was incredibly well instrumented. That was not taken out of the build cycle. All those diagnostics were kept in, and they were used extensively. Probably the one thing, as you go through re-engineering, you're going to realize steady state designs aren't steady state in the real world. That whole point design that we look at, that doesn't work either. At some point in time, there's always variations. This is an environment, quality of supplies. Is it a hot day? Is it a humid day? Is it a dry day? Is it wind blowing? Is there dust in the air? Something's going to change. Maybe it's raining outside. Supplies. How's my chilled water? Has it been treated properly? Is my filter that I just put into it a good one, or did it have a little manufacturing issue? Does my natural gas have a high BTU content today, or does it have a low BTU content today? Those all create variations. But with the proper instrumentation and anticipating that in the design phase, when you ask yourself, what if in the use cases, that leads to, if this happens, how do I know? You'll know where to instrument. You're going to need to know what happens. You can't go out and check everything. You want to automate it. Putting this much money into a resilient solution, don't scrimp on the data structure. You really have to have that instrumentation to really look at the variations on day-to-day. Most of these projects, whether they're in a university, whether they're in a commercial industrial setting, a government setting, a military setting, they're going to have a burn-in time. 30 days, 3 months, not unusual. You're going to have to go through that, and you're going to want to see this data. It's absolutely essential to have that data for the operating optimization. Our investigation of the determined really highlighted 3 areas of concern. Was cleaning. Cleaning was inadequate, by the way. I mean, it just in the manufacturer to recommend a cleaning cycle. Given the situation we were in, given the environment we were in, given the location we were in, that didn't work out so well for us. Inlet air filtering, they had their standard filter. We had to go put it quite a bit better. Again, environmental conditions changed what we needed to do for the filtering. We actually added a filter, a pre-filter to take out most of the particulate matter, and then a fine filter which reduced it even further, obviously. Inlet temperature, we designed for 59 degrees. The chilled water system did not always hit that. We pulled the water from the chilled water system. It has a temperature control question on it. So it varies a little bit. Okay, not a lot, but a degree or two does mean something. So, but we were instrumented well enough, we knew what to look for. As you go through this, you can see the early, you can see my cursor, we operated below what we expected to. We got up here finally, and then it started to degrade. We cleaned it and we go, well, maybe our cleaning isn't frequently enough. Okay, so we see it kind of varying a little bit. Well, something else is going on. Air temperature inlet control, we started to tighten that up. So, it's still not right. The air filtration was improved. Once we did the air temperature control as far as the inlet temperature from the inlet temperature of 59 degrees, air filtration was improved. Then we did weekly and online cleaning, where then we started to meet what we said. But in here, we missed, which means we wrote a check. Fortunately, very fortunately, we have people on staff that actually understood this, have been through this, have lived this, and got with the data. We were able to close this out pretty quickly. So we knew where it was, we fixed it, and kept on going. We just changed our operating procedures. Experience counts. Lessons learned. Steady state designs aren't. They're going to vary every day. You really, I can't I probably said this half a dozen times already. Don't take out the instrumentation. If you're the design engineer, if you're the operations guy who's going to put this into play, if you're the guy who's going to maintain it for X number of years, imagine you have a problem and what data do you need to fix that problem, and play the what if games. Then you'll have it instrumented enough because you would go back and this is what I want to see. It also is a cheap insurance policy. Understand the impact of your environment. You really got to say, am I dusty? Am I not dusty? Where can I take it out? How do I want this to operate? Frequently, we want to look at the first level effects. You really can't do that. You got to look at second and third order effects. Where am I going to go with this? How is it going to operate? People are counting on this critical facility that you're installing to operate within the bounds, just like a utility, if that happens to be the case. They expect that same level of diligence and what can go wrong, what do I have to consider, and that's where you're going to go. That's not just first order, it's second and third order. And again, experience does count in the debugging. So, closing up, longer than I thought, resiliency must be viewed holistically. You need to treat it as a system. It is very much a collaborative design. All the stakeholders, and probably some I didn't say, need to be involved. What are the requirements? Everything's based off requirements. You go with a canned solution, you may lose, you may miss, you may not have what you want. certainly the customer's not going to get what he wants typically. The customer may tell you, I want a microgrid. That may not be exactly what he needs. So careful with definitions. Make use of any available options you have. Understand what's there. Understand where you want to be. That's the gap analysis. And that's what you have to fill, is that gap. You can group the buildings by functions and by electrical feeds. Use cases that can't over, the thought experiments, the what ifs, plotting them out, keeping track of them, what's going to happen. Cybersecurity, you really have to design in. It's much like I worked in the semiconductor industry for quite a while. You can't add cleanliness to a system. You can only design it in. Cyber is very much the same way. You can add it to Band-Aid, and it's probably not going to last. Design it in. Make sure you understand it. Make sure you have it covered. Controls. Again, they need to be modifiable and flexible over time. It can't be, hey, this is it, and walk away. It's going to change over the life of those assets, and those assets last a very long time. Think back 10, 15 years ago what the operating system was, and now think forward. What's it going to be? We don't know. But we know that we're going to have to continue to use these assets in some fashion. And again, I'll reiterate, steady state designs aren't steady state. Cheyenne, that's what I've got. I have a few minutes for questions. I can stay on a little bit longer if people like, so turn it back to you.
Right. Thank you. We'll start with the first question. It is, everyone is talking about the new norm. How will this affect facilities' energy consumption since corporations are encouraging working from home culture for certain workforce?
Some people can work from home. Certainly I do, to be honest with you. I don't go to an office. I work from home. There are certain facilities that cannot work from home. There'll always be some critical mission functions that are in brick and mortar stores. Is it going to help with the energy efficiency? The answer is, if you take a look at where you're getting power from a utility right now, and I move that onto a site, I have a 35% efficient turbine on site, maybe it's 40%, we can argue efficiencies. I put 1,000 BTUs in, I get 350 to 400 out. I then transmit it, I lose more. I'm down to 250 when I get to the site. If I put CHP on site, I probably get 700 out of that. As I go back to distributed generation, my efficiency actually goes up quite a bit. If I integrate that with renewables, it gets better. So the question becomes, are people going to go off the new normal and work from off-site? The answer is yes. Are you going to be able to do this at all the facilities? The answer is no. We're on those critical facilities where you can't move those buildings, where you can't move that function for whatever happens to be the reason. The answer is you're going to need this. So I'm not sure I answered it totally, but that's kind of where I'm at on the new normal.
Thank you. The next question is, can we relate this to commissioning of building energy systems?
It's not a lot different when you say, building energy systems form the heart of the commissioning process should be fairly identical. As you commission a building, whether you're doing an energy systems, HVAC, you're going to add chillers, boilers, HVAC, rooftop units, whatever, a building management system. The same thought processes should be used no matter what problem you're going after. As you go through, you're going to ask the questions, what do I need to do? Am I going to over-design it? Which is what typically happens. A lot of the boilers we're replacing now we're replacing with 2 or 3 because they're now being right-sized. The commissioning process of that goes down again. The philosophy shouldn't change. Philosophy should be, I'm going to commission at the lowest possible subsystem level I can. And whether that's a control point, whether that's a repeater system, whether that's the actuator, opening and closing, or whether it's just on how the closed loop system reacts. This all relates back into the same type of system that you're talking about. Whether it's resiliency is a very particular question. The process should be the same or very nearly the same for any building that you're going to put together. You just have multiple floors or multiple rooms.
Thank you. The next question is, what is the best way to get trained in resiliency? Does one need to be an engineer?
To go into the details of the engineering aspects of it, yeah. To get trained in resiliency, the answer is no. A lot of this is done or can be done. There's training sessions like this with AEE. There are other ones that are, I mean, certainly energy, there's other conferences that hold and have a lot of resiliency aspects to it. Several publications out there online give you weekly or daily newsletters and also talk about it. I'm not sure the best other than getting into industries that actually deal with that, whether that's an engineering design firm, whether that's an ESCO like Energy Systems Group or others, or our competitors, or is it working with the, the government, local governments as an energy manager. If you're not an engineer, there's going to be some hampering to that, but not a lot. You just have to kind of dig in and learn a little bit. You won't do the math more than likely, but you certainly understand the concepts and how they all work together.
Thank you. And just to respect everyone's time, we will stop with questions there. However, if you have any more, please feel free to email myself and I will forward them along. And I am just going to wrap up with a few final announcements from AEE. So again, if you are interested in obtaining a copy of this presentation, please send me an email at cheyenne@aeecenter.org. And also as a reminder, you will receive an email this week with your attendance certificate and a recording of the webinar. Last week, we announced that our AEE West Energy Conference and Expo, originally being held in Seattle, Washington, would now be a full virtual event. The event will be held on June 23rd through 25th. It will feature keynote speakers, technical sessions, a full virtual expo hall, and plenty of networking opportunities. Registration is now open and it is only $49 for AEE members. To register or for more information, please visit west.aeecenter.org. Additionally, AEE World, held in Denver, Colorado on September 23rd and through the 25th, is currently scheduled as normal. We will be monitoring the situation and continuing to provide you with any updates. AEE is continuing to offer online training and remote proctoring. We are always adding new training opportunities, so please make sure to check our website for updates. There will be a live CEM course in Atlanta starting June 1st and another live CEM course in Minneapolis starting on June 15th. We will be continuing to offer our 3 different webinar series, our AE East series, our monthly member webinars, and our COVID-19 series. You can view the full schedule and register for upcoming webinars under the Member Benefits tab on our website. Our June webinar schedule will be added this week as well. Our next webinar will be held on Wednesday, May 27th on the future of roofing and outdoor lighting infrastructure with Bluetooth mesh networking. Again, thank you to Mr. Taylor and to all of our attendees. Please stay safe, and I hope you all have a wonderful day. Thank you.